Hello everyone, welcome again to Modeling Methods in Mechanical Engineering, and today we're going to continue our discussion on differential equations, in particular ordinary differential equations. And today we're going to increase the order of the differential equations that we have been actually studying in this class. And we're going to talk now about second order differential equations, which in engineering and science govern a wider spectrum of problems. So up until now, we had seen how to address first order differential equations, those in which the highest derivative is the first derivative. And we talked about the fact that there are many problems in engineering that are governed by such equations. And so we looked at ways to solve these equations analytically, as well as ways to approximate the solution numerically. Now, it turns out, as I mentioned in class, that there are a wider range of problems that are governed by second order equations in engineering. And with second order equations, we can establish a difference between initial value problems if the equation depends on time, if the field variable that you're solving for depends on time, or boundary value problem if the field variable that you're solving for depends on space. So we address the equation the same exact way, but at the moment of actually imposing the conditions, whether they are initial conditions or boundary conditions, it makes a slight difference. So Let's talk about these equations, and today we're going to discuss an analytical technique to get to the answer. So these are a little bit modeling methods in ME. And we're going to talk about second order ODEs. So let's start with a general expression for these equations. So in general, a second order linear constant coefficient homogeneous ODE can be written as, and as you can see, we're confining our illustration today to just linear constant coefficient homogeneous second order ODEs, which again can be written as a times d second y dt squared plus b dy dt plus c y of t is equal to 0. So basically this is, as I said, a linear equation, so linear combination of derivatives and of the field variable. Then constant coefficients, the coefficients that multiply these derivatives of the field variable are constants, not functions of time. Homogeneous, so there's no independent term, this is equal to 0. And the second order, obviously the highest derivative in the equation is the second order derivative. So in order to solve this equation, we can formulate what's called an auxiliary problem. Can be set up to determine a non-trivial solution based on the roots. So we find the roots m1 and m2 based on coefficients a, b, c, as if this were a quadratic equation. It turns out that the auxiliary problem ends up giving you a quadratic equation for the eigenvalues for a non-trivial solution, and these roots just follow the quadratic roots, just as that. So basically the general solution y of t depends on the nature of these roots m1 and 2. So depending on what those roots are, if they're real, they're complex, or they are repeated, or purely imaginary, the solution is going to look slightly different. At the end, it's just the same solution. It's just that with some transformations, we can make it look slightly different. So if M1, N2 are real and different, so if both M1 and M2 are real and they're different from each other, that means that that number is not 0. If these numbers are 0, then the two roots are repeated. Minus b over 2a are the same. So basically, if b squared minus 4ac is greater than 0, so if that argument and the square root is greater than 0, then the solution y of t would look like c1 times e to the m1t plus c2 times e to the m2t. By the way, these can also be written in terms of sine hyperbolic and cosine hyperbolic. It actually comes out to be an equivalent expression. So we're going to write it that way. So we find the roots, and if they happen to be real roots and distinct or different, then that's how the answer to that equation would look like. And you can try it. You can take that as a general solution. And notice that the general solution has two constants of integration because this is a second order equation. You can try this, take the first derivative, the second derivative, plug it in here, and you will see that it resolves to 0. So 2 if M1 and 2 are real and repeated. That is, if b squared minus 4ac is equal to 0. So it's exactly equal to 0. Then the solution y of t will look like c1 times e to the mt plus c2 times t times e to the mt, such that m is m1 and m2, which are the same in this case. So this is case number 2. Again, you can prove that this is an answer to the equation in the event that b squared minus 4ac is equal to 0. Very easily, actually. Now, if m1 and 2 are complex and conjugate, which they come in pairs, so basically b squared minus 4ac is less than 0, then we can express the solution y of t as e to the alpha t times c1 times the cosine of beta t plus c2 times the sine of beta t such that m1 and 2 is equal to alpha plus minus I beta. So remember that complex solutions in a quadratic equation come in conjugate pairs. This is the real part of the complex number. Beta is the imaginary part of the complex number. And they come in complex pair, pretty much essentially the real part plus minus the imaginary part, always. So if that's the case, this is how the solution looks like. And you can pretty much see what happens when alpha is equal to 0. So when alpha is equal to 0, when there's no real part, so the solution is purely imaginary, then this will go to 1, and you end up with a purely trigonometric solution. So essentially a wave solution with no decay or no amplification. So these are essentially the three options of what the solution of a second order ODE that is linear, constant coefficient, and homogeneous would look like. Now notice again that the constants of integration, C1 and C2, can be determined like this. By imposing two initial conditions. So basically, for the initial value problem to be well posed, we need to define, so the ODE needs to be fully defined, and we need to have a pair of initial conditions so that we are able to determine the two resulting constants of integration. The first one is, well, what is the field variable at time equals 0? And the other one is, what is the derivative with respect to time of the field variable at time equals 0? So we can call that position 0 and velocity 0. If y is actually a position, then dy dt would be a velocity. So this conforms what we call an initial value problem. Initial value problem. Or, in the event that the ODE field variable is a function of space, so i.e. y of x, then we need boundary conditions at both ends of the domain. So going from 0 to L, for example, if x goes from 0 to L, we need a condition at 0 and we need a condition at L. So the way this works is that, let's go to another page. So if this equation happens to be an equation of in terms of space, so where instead of time derivatives we have space derivatives. So let's say that we're solving for the temperature distribution on a linear bar or in a pipe along the axis, and then we formulate these in terms of an equation, a second order equation of the temperature as a function of space x, and it turns out to be a second order equation that we can solve in this particular way. Then the solution will be in terms of y of x, and we need, in order to find the constants of integration C1 and C2, we need what's so-called boundary conditions. So these boundary conditions, let me see if I can fit them here. We need a condition at x equals 0, and we need a condition at x equal L. So we need either y at 0 is equal to y0, or something like dy dx at 0 is equal to q0, or dy dx at 0 plus some coefficient h times y at 0 is equal to t0, and we need a condition of y equal L. So we need y at L is equal to yL, or dy dx at L is equal to qL, or dy dx at L plus h at yL is equal to some TL. So we need a condition at x equals 0 and a condition at x equal L. So these are 9 possible combinations of conditions. We can have the value of the field variable at 0 and the value of the field variable at L. We can have the value of the field variable at x equals 0 and the derivative of the field variable at y equal L. We can have the value of the field variable at x equals 0 and a combination of the derivative and the field variable at x equal, and by the way, this h is also given, whatever that is. So we can, as you can see, we can have 9 possible combinations of boundary conditions. These are called first kind boundary conditions, second kind boundary conditions, and third kind boundary conditions. Okay, so these y is equal to some y is called first kind. Dirichlet or forced BC. So when we impose dy dx is equal to some given value q, this is called a second kind Neumann or natural boundary condition. Or when we impose the ratio dy dx plus h y is equal to some given number t. That doesn't have to be a temperature, it's just a t, a number, a given number. This is called the third kind Robin or convective BC. So we have three possible boundary conditions at each end, which gives you a nine possibilities of combinations of boundary conditions at both ends. But in order for the boundary value problem, the ODE and boundary condition combination at x equals 0 and x equal L forms a well-posed boundary value problem instead of an initial value problem, for which you need initial conditions, 2 in this case. So here you still need 2 conditions, right? One at x equals 0 and one at x equal L, but those conditions can be a combination of different things. But you still have to, for the problem, for the VVP, this is a boundary value problem, VVP. For the VVP to be well posed, you need to have a condition, a single condition at x equals 0 and a single condition at x equal L. All right? So for the boundary value problem to be well posed and solvable, and to yield a unique and existent solution, we need a single boundary condition at x equals 0 and a single boundary condition at x equal L. Okay, and when I say single, I'm not talking about a first kind condition. I can have these at x equals 0 and this at x equal L, and that's perfectly solvable. Okay, and we'll get to that as we broach more into boundary value problems. But for now, let's just concentrate on the problem at hand. We're trying to solve a second order differential equation, second order ODE that's linear, constant coefficient, and homogeneous. And again, that equation can be a function of space, or it can be a function of time, or the field variable itself can be a function of space or a function of time. All right. So now what if the ODE is non-homogeneous? That is, again, let's continue to discuss this in terms of time. So this is an initial value problem, so the differential equation that's a function of time. So we still have a second order equation that's linear and that's constant coefficient, but now we have an independent term on the right hand side, RT. Okay, now this solution, that can be a constant, by the way. Anything that's other than 0 will make this equation non-homogeneous. Now the solution y of t highly depends on the nature, on the algebraic form of the forcing function R of t. That is, if the forcing function is a trigonometric function, we expect the solution to be sort of trigonometric. If this function happens to be logarithmic, we expect the solution to follow a logarithmic form, and so on and so forth. So the solution yt may be separated into a homogeneous part and a specific part. In other words, we can solve this equation first as if it were homogeneous. So we can put a 0 here and then solve that equation, which we know what to do, find the roots and determine the nature of the roots, and then basically say it's exponential or trigonometric or a combination of the two. All right, so we're going to say y of t is equal to some homogeneous part plus some specific part. So the homogeneous part is going to respond to the homogeneous version of this equation, and the specific part is going to respond to the nature of what this forcing function r of t is. The given forcing function, remember, that's part of the equation and therefore is a given. So such that yh of t satisfies the homogeneous version of the equation, which is simply this. So we solve that equation, which we know how to solve perfectly. Again, find the roots and determine what the roots are, and so that is this part of the solution. So find yh of t using the methodology described above, that we just described. While the specific solution part of the solution, ys of t, will depend on the algebraic form of the forcing function. RT. So that is, let's just try to summarize this in a table, but obviously there's literally infinite possibilities for what that function r of t could be. It can be any form, but I'm going to list the most common ones here. So if r of t is, then you're going to let, I'm going to put in a divider here. So we're going to let ys of t be. So 1, if it's a polynomial of degree n, so let's say i.e. y, I'm sorry, not y, this will be r of t, this is an r, is equal to 3t squared, for example. This is an example. It's a polynomial of degree 2 in this case. Then let ys t be a polynomial of degree n, but the full version of the polynomial. So for example, if r of t is 3t squared, then ys of t will be k0 plus k1t plus k2 t squared. So a full polynomial of order 2, including the terms that are not present in the polynomial, all of them. Okay. 2, so it's an exponential with argument lambda, for instance. Then y of s is going to be k0 times e to the lambda t. So for example, if r of t is 4 times e to the minus 2t, we expect then that the solution ys of t should be k0 times e to the minus 2t. Should be exponential with the same argument minus 2. Not the constant that multiplies the exponential. We'll replace that by an unknown parameter k0. 3. Trigonometric with argument, or in this case wavelength, omega. Then ys should be k0 times the cosine of omega t plus k1 times the sine of omega t. So, for example, if RT happens to be equal to, for example, 2 cosines of 3t, that's the forcing function, then ys of t will be k0 times the cosine of 3t and k1 times the sine of 3t. You have to include both trigonometric functions if the forcing function, even if the forcing function only has a cosine or a sine, then the expected specific solution has to have both versions of the trigonometric function. For another example, an exponential trigonometric with arguments lambda and omega, then we expect the specific solution to also be trigonometric and exponential. With the same arguments, lambda and constant and omega. So for example, I'll give you more space here. If RT is 4e to the minus 3t times the sine of 2t, so that is the forcing function, then the specific portion of the solution is equal to e to the minus 3t, so we keep the same exponential argument, times k0 times cosine of 2t, the same wavelength for the trigonometric function, plus k1 times the sine of 2t. And again, these are just 4 of the most common types of forcing functions. Again, there's literally an infinite number of possible options for what the forcing function r of t could be, but these are the most occurring ones, so we'll confine it to those. Now, what we end up with is a function y of s that is that depends on these new parameters k0 through kn, for example. So these coefficients, the coefficients k0 through kn, are found by using the method of undetermined coefficients. Basically by introducing ys of t into the ODE, grouping common terms, and formulating a set of algebraic equations for the coefficients, for these unknown coefficients. So we basically, what we do is take this y of s, whatever it is, in terms of these new coefficients k0 through kn, plug them into the original equation. This is y of s of t plus b. Remember, a, b, c, and r are known. dys t dt plus c ys of t is equal to R of t. So we basically take this solution that we just guessed, this trial solution, differentiate it once, differentiate it twice, plug it in here, and then combine terms of equal nature on the left and compare them to those terms on the right. And that way we will formulate these set of algebraic equations for the coefficients k0 through kn. Right? So for example, if this solution, if R of t is a trigonometric solution, a trigonometric function like this, then we use a trial function, ys, k0 cosine of 3t plus k1 sine of 3t, right? Then we take the derivative of these, which will have a sine and a cosine, and we take the second derivative of these, which will have a cosine and a sine. We plug them together, we plug them here, here, and here. We multiply by the given coefficients of the ODE A, B, C, and then we group all the cosine terms together. So this is going to have some cosines, this one's going to have some cosines, and this one's going to have some cosines. And whatever's multiplying the cosine here, we equate it to whatever's multiplying the cosine on R of t. So R of t was originally 2 times the cosine of 3t. So whatever's multiplying the cosine here is going to be equal to 2, right? And then we group whatever's multiplying the sine. So this one's going to have a sine, k1 times the sine of 3t. This one's going to have a sine, right? So when we differentiate this, this is going to be minus k0 omega times the sine of omega t. And this one's going to have a sine. This will be k1 negative times omega squared times the sine of omega t. And we multiply times a, b, and c. Then we group together whatever's multiplying that sine of omega t. And whatever multiplies that sine of omega t, we equate to whatever multiplies the sine of omega t on the right-hand side, which in this case, this is a function that was given, nothing is multiplying the sine. So whatever multiplies the sine on the left-hand side is equal to 0. And at the end, that will give us a set of 2 equations for with two unknowns for k0 and k1. Very simple. And the same thing will work out for whatever combination or whatever algebraic form the original forcing function R of t is. All right. So this is what that's where I'm gonna stop right now. And next class, what we're going to do is we are going to get together and try to see if we can figure out a way to solve these numerically, to approximate the solution. Again, this is an analytical solution, an analytical method, but it's confined to a very specific case, a very simple case where the equation is a constant coefficient, is linear, is homogeneous, well, in this case it's non-homogeneous, but we'll see what happens when we, for example, have variable coefficients and see if we can address that solution. And then we'll solve an example and then compare the analytical to the numerical solution and see how the numerical scheme behaves. So that's it for today. So thank you for your attention, and I'll see you next class.